So we can do that manually, but what we'd like to do is we'd like to specify those operations automatically. And we can do that in the Java programming language. So it turns out that in the Java programming language, here is some code that has Becky go pick up the bagel in front of her door. So everything in Java is modularized into entities called classes. So it turns out there's a generic Buggle world that we saw before, and this breakfast world extends Buggle world in the sense that it does everything that Buggle world does, plus it does more. In particular, it defines Becky's actions to go pick up her morning bagel. And inside this breakfast world, we define a method called run. So a method is a collection of instructions that we can put together. And if we take a look at this collection of instructions, we see that the first thing we do is we create a Buggle named Becky. And we'll explain this exactly what this is called the syntax of the language, how we put together particular programming phrases. But let's just kind of read it like English for now. We create a Buggle named Becky. We create a Buggle named Becky. And then we send Becky forward 2 positions. We send her left, forward, right, left, and then forward 2 more positions, and then she's in a position where she can pick up the bagel. So this now is a sequence of instructions. We now created a Buggle named Becky and given her instructions of how she should go pick up that bagel. And we should now be able to go and run these instructions. So if we go back to our world over here and we reload our world, it turns out that when we press the run button down here in Buggle world, that it executes all of those instructions that are in that run method. So here if we press run, look what happens. Becky is created. She follows all the instructions. She ends up over the bagel, and the bagel gets eaten. And that's wonderful. Okay, so we've now seen our first Java program. But there's a question. Suppose the bagel isn't at the same position every morning. What happens then? Well, for instance, it turns out that in our program, if we hit reset, then the bagel can be placed at a different position. So now if we run the very same set of steps that we did before, Becky ends up overshooting the bagel. And in fact, if we look at our console here, it complains that there's no bagel to pick up because she didn't end up at the right spot. And in fact, if we keep on resetting here, we can have her have the same problem again. Here, she's going to go too short. And let's suppose the bagel delivery person, accidentally leaves it on top of the house. There's no way that she's going to find it. So what we'd like to do is we would like to be able to describe more general algorithms, that is computational recipes, by which Becky could go off and find the bagel no matter where the bagel delivery guy drops it off. And that's the kind of problem or puzzle that we're going to solve a lot in this course. So let's just say a little bit more about how computer languages are executed. It turns out that inside the computer is a microprocessor chip that executes a very low-level computer language. So that low-level language differs from chip to chip, but it has instructions that look like this: load R4A, load R5B. And what this means is I want to stick the value that's in the variable A into register 4. I want to stick the value in B into register 5. I then want to add the values in register 4 and register 5 and stick the result in register 4. And then I'm going to store the result of register 4 back in the variable C. So what that's doing is that's storing the sum of the variables A and B and putting it into variable C. And that's a very low-level way of saying that. Java is what's called a high-level language. If we want to say that we want to store the sum of A and B into the variable C, then in Java we would write the same program as C, is assigned the value of a plus b, or C gets a plus b. We don't read this as an equal sign. We read it as assigns or gets. And so that's a different way to write the same thing that's in this other program. And to get from this high-level language of Java to the low-level language of the computer, we need some sort of translation. And there are two kinds of ways that translation can occur. So if you think about how things work in the United Nations, people are speaking in different languages, and we have a bunch of translators who are translating those languages, what they're saying on the fly. And a translation on the fly is known as interpretation. So an interpreter is something that can take a program like this Java program here, and it can directly run each of the statements that's in that program. So when we see Buggle Ben is a new Buggle, the interpreter says, aha, I want to create a new Buggle. And when we say Ben.left, it says, aha, I want to take that Buggle I just created named Ben and turn Ben so that he turns to the left, and so on. And so that's how an interpreter works. An interpreter takes each statement one at a time and does what's suggested by those statements. There's another strategy for implementing computer languages called a compiler. And in a compiler, it's much more like translating a book, say, where you have the entire book and you get to translate it, and then no one reads it until you're finished with the translation. So a compiler is just a translator. It takes a program like this guy over here, and it translates it into some low-level language. Now, the low-level language, we often say that computers run the low-level languages based on zeros and ones. That's actually not really a very helpful model. It turns out that these zeros and ones really stand for, if we go back a few pages, those zeros and ones really stand for things like loads and stores. They're just written in a language that's kind of hard to read. But each one of these lines might refer to loading or storing things in particular registers or variables. But the point is it's some low-level language. And then that low-level language gets executed, say, by the microprocessor that's sitting in your computer, which we'll call an object code interpreter. And then when it executes it, it ends up doing the same thing that the high-level program would have done, such as creating some particular diagram here. It turns out that Java uses a combination of both of these strategies, so that when you take a Java program, you first compile it. But you don't compile it into a very low-level language. You compile it into a somewhat middle-level language. That middle-level language is called a .class file. And I'm not going to show you exactly what a .class file looks like, but it has some stuff in it that looks a little gibberishish. And that .class file can be executed by something called a Java virtual machine. And the Java virtual machine goes off and has the results that you might expect. And the interesting thing about using an intermediate code, such as in this .class file, is that we can compile the Java program once, and then we can run that compiled program on many different machines. Normally, you didn't need a different compiler to compile things for different machines, but in Java, we have only one compiler that compiles to a .class file, and then we have different JVMs or Java virtual machines on different computers that's running that code. In this course, you'll be doing a lot of programming, and you will be doing it in a particular programming environment called Dr. Java, and you will see this in your Wednesday lab. Let's just take a very quick look right now. I'm going to open up Dr. Java. Dr. Java is an environment in which we can type our code and execute it. So it turns out I've typed in the code here for the run method that Becky uses. And we can compile our code. I press a little compile button here. I can then press a run button, and then when we actually run the code, it goes off and it executes it. It also turns out that, just so you know, if we go off and compile and run our program again, rather than hitting the run button, we can also hit the step button inside of Buggle World. If we hit the step button, it does one step at a time. So notice down here it says we've created a new Buggle. If we do a step again, we went forward 2. We did another step, we went left. We do another step forward, and so on. And so we can go step by step through our program to see what it's doing. And that can help us figure out when a program doesn't work. So programs that don't work are said to have bugs. And when we try and find what the bug or problem with our code is, we are said to be debugging. And this kind of information here is very helpful for debugging. Okay, so that's our introduction to CS111 and Java. We'll end with some examples of some of the other worlds that we use and the kinds of problems that we will solve. These are in the CS111 museum, which you can find on the CS111 homepage. Let's just click the link here. So for example, in Buggle World, here's something that we might want to do. We might want to have this program called Dead End World, where every time that the Buggle reaches a dead end, it drops a bagel. So a dead end is a spot that's surrounded on 3 sides by a wall. So here we have a Buggle that's going through a grid and then dropping a Buggle in every dead end. And this is the kind of problem that you will end up being able to solve in this world. And there's lots of interesting Buggle problems that we can have. So I'm going to stop this here. There's another world that we have called Picture World. And Picture World is a world in which we can create interesting patterns. So here are some interesting knitting patterns that were created by Dutch artist M.C. Escher. And they look very interesting. They look like different ways of knitting different colored yarns together. What may not at all be obvious is that all of these knitting patterns that were just displayed, in fact, are created out of 2 very simple patterns. So there's this pattern here, and then there's this pattern here, which is almost the same, except that certain things appear to be over or under in one pattern that are different in the other pattern. It turns out if you take this pattern, this A and B pattern, and you color the parts differently, and you flip and rotate and glue these parts together, you can get all of the different knitting patterns that we saw. So each of these different knitting patterns here is made out of the same pieces using different colorings and flippings and rotations. And that's really amazing, and you're going to get a chance to play with this. And Picture World's a really fun environment in which to create interesting pictures and solve problems. A cousin of the Buggle is something called a turtle. And here we're going to have a turtle that's going to go off and draw trees. So we're going to specify some parameters here of how the turtle should go off and draw a tree. We'll have a whole lecture on this later in the semester. And when we run this, it goes off and creates a tree-like pattern that's recursive. And if we go off and we change something like an angle over here, set an angle to be 20 rather than 30, and we run this, then we get a different picture. If we set the angle to be much larger, say we set the angle to be 90, we get a picture like that. And one of the final microworlds that you will look at in this course is something called Animation World, where you can make your own animations. For instance, here is an animation made by Smaranda Sandhu, who's one of our TAs this semester. If we play her animation, we see a flying bee here going around and creating CS111 flowers on a CS230 flower. This is kind of a fun and complicated thing. That's what we have. And these are the kinds of worlds that we'll be working on and solving problems in. And I encourage you to go and explore the CS111 website and to look at the museum and see what other kinds of worlds are in there. And just explore. One of the things you should do most in this course is never be afraid to explore. And we look forward to exploring with you. Thanks a lot for your attention.